Hey there, and welcome. When you see a math problem that's just full of those little root symbols and you feel a bit stuck? Well, you're in exactly the right place. Today, we're going to break down how to work with radicals and show you just how simple they can be once you know the rules. All right, let's jump right in. All right, so take a look at this. At first glance, you might think, no way, you can't add those. And you'd be right, kind of. In the form they're in right now, you can't. But by the end of this, you'll have the key to unlock problems just like this one. And you'll see it's actually way easier than it looks. So here's the plan. We're going to start with the absolute basics, build our way up through the different operations, and then, and this is the cool part, we'll see how it all clicks together in a real-world problem. It's a step-by-step journey, and we're going to cover it all. Okay, first things first. Before we can do anything cool, we gotta speak the language, right? Understanding the different parts of a radical is, well, it's the foundation for everything that's coming next. So, before we start crunching numbers, let's get our vocabulary straight. Think about any radical expression you've seen. That number sitting out front, being multiplied, that's your coefficient. The tiny little number tucked into the checkmark part, that's the index. It tells you what kind of root you're dealing with, like a square root or a cube root, and the number inside the symbol, that's the radicand. So coefficient, index, radicand. Got it? These three are going to be our best friends today. Okay, let's ease into this with some easy wins. Seriously, multiplication and division are super straightforward. They follow one simple, intuitive rule, and it's a great way to build up some confidence. Okay, here it is, the first big rule. As long as you're multiplying radicals that have the same index, like two square roots, you can just smush them together. You multiply the numbers inside, the radicands, and pop the answer under one big radical sign. That's it. It's really that simple. Check out this example. It's perfect. The square root of 3 and the square root of 12. I mean, on their own, they're kind of messy, right? But using our new rule, we just do 3 times 12, which is 36. And what's the square root of 36? It's 6. A nice, clean whole number. Ah, so satisfying. And you know what? No surprises here. Division works pretty much the exact same way. If you're dividing two radicals and their indices match, you can just combine them into one big radical and divide the numbers inside. Easy peasy. So, for example, the square root of 40 divided by the square root of 5, well, that just becomes the square root of 40 divided by 5, and that's the square root of 8. Now hold that thought because we can actually simplify the square root of 8 even more. We're going to get to exactly how to do that in just a minute. All right, time for the main event, adding and subtracting. This is where the real skill comes into play. But I promise, once you get this, you've basically mastered the core of working with radicals. So what's the secret? Honestly, just think back to basic algebra. You can only combine like terms, right? It's the same thing here. Just like 5x plus 2x is 7x, well, 5 times the square root of 2 plus 2 times the square root of 2 is 7 times the square root of 2. See? The radical part, the square root of 2, it just acts like the x. As long as it's identical, you just add or subtract the numbers out front, the coefficients. Okay, that's great, but what happens when the radicals are not like terms? This brings us right back to that problem from the very beginning. Square root of 50 plus the square root of 18. The insides are different, so we can't just add them. What on earth do we do? This right here is the magic trick. It's all about simplification. The whole idea is that we simplify the radicals first. And when we do that, a lot of the time we find out they were like radicals in disguise the whole time. This is, without a doubt, the most important skill you need for adding and subtracting. Okay, let's walk through this with the square root of 50. Step 1. We break 50 down into its prime factors. So, 50 is 2 times 5 times 5. Step 2. Since this is a square root, we're looking for pairs. And look, we've got a pair of 5s. Step 3. For every pair you find inside, one of them gets to escape and go to the outside of the radical. Step 4, what's left over? That lonely 2? It's stuck inside. So the result? The square root of 50 is the same thing as 5 times the square root of 2. And now we can finally solve that first problem. We just figured out that the square root of 50 is really 5 root 2. Now, if you do the same exact thing for the square root of 18, which is 2 times 3 times 3, you'll find a pair of 3s. So that simplifies to 3 root 2. And would you look at that? All of a sudden, we have like radicals. 5 root 2 plus 3 root 2, that's just 8 root 2. Problem solved. All right, let's quickly level up with 2 more rules. They look kind of fancy, but they're actually super simple.
So what happens if you have to raise a whole radical expression to a power? It looks scary, but don't worry. The rule is dead simple. You just take that power from the outside and move it to the inside and apply it directly to the radicand. The index stays the same. That's it.
And what about this crazy thing, a root of a root? This is even easier. You just multiply the two indices together. So a cube root of a square root, you just do 3 times 2, it becomes a single sixth root. It's literally just a multiplication problem.
Okay, let's tackle a topic that sometimes trips people up: rationalizing the denominator. Now, this isn't really about changing the value of a number. Think of it more like mathematical etiquette. It's just the proper, standard way to write your final answer.
So here's the deal. In math, it's just considered kind of messy to leave a radical in the denominator of a fraction. So how do we clean it up? Simple. We multiply both the top and the bottom of the fraction by whatever that radical is. Now, why does that work? Well, think about it. A square root times itself just cancels out the root. So if you have 2 over the square root of 10, you multiply the top and bottom by the square root of 10. On top, you get 2 root 10. And on the bottom, root 10 times root 10 just gives you a nice clean 10. No more radical in the denominator.
Okay, so we've got all these rules down. But so what? What's the point of all this? Let's take a look at how all these skills can actually come together to solve a real practical problem.
Okay, check this out. We've got a simple rectangle, but its side lengths aren't nice whole numbers. They're radicals. We need to find the perimeter. So how do we do it? Well, we're going to use everything we've just talked about.
Okay, let's walk through it. Perimeter is all the sides added up, right? But we can't just add root 8 and root 32 yet. They're not like terms. So what's our first step? You guessed it, simplify. The square root of 8 simplifies down to 2 root 2, and the square root of 32 simplifies to 4 root 2. And now they're like terms. We add them up to get 6 root 2, but that's only half the perimeter, so we multiply by 2, and our final answer is 12 root 2. See? It all comes back to simplifying first.
You know, from the Pythagorean theorem that helps build our houses to calculating distances in physics, radicals are, well, they're everywhere. They're a fundamental piece of the language we use to describe the world around us. Now that you know how to speak that language, the only question left is, where are you going to spot them next?